going to go ahead and go through some problems that might be helpful. This is the review that I put up for extra credit, but I'm going to go through kind of these and talk through them. And then just kind of look through here. We didn't talk about complement, just reminding you what a complement is. If the probability of A is 0.4, the probability of the complement of A, which you put a C there, or you can do this, is going to be just 1 minus 0.4. It's just the opposite of it. So it'd be like raining, probability of raining and not raining. They're completely opposite from each other. We talked about disjoint. The general addition rule is the probability of A given B is the probability of A and B over the probability of B. And that's for, and then for probability of A or B, it's the probability of A times the probability, or sorry, plus the probability of B minus the overlap, A and B. So these are the general rules. This one's multiplication, this one's addition, but doesn't matter, it's just a general rule. Intersection, of course, is A and B, it's just that intersection. Union is both of them together, and that's A or B. And obviously the biggest thing to do is if you were to have the green one plus the purple one is to make sure that you subtracted this overlap right here. Let's do, of course, we talked about all these in my first videos. The general multiplication rule I just talked about. I showed you both the multiplication and the addition rule. Independent events, we talked about this in my first video, so if you, and conditional, you can go through my video and watch that. I think that's on video 1. We can go, I guess I can do this one if you want. Oh, I can do this. All right, so this is a relationship between gender and candy preference. As opposed 200 high school students were asked to complete a survey. So this is what we're going to do. We're just going to say is the relationship between gender and candy preference if the probability of, let's say, male given Skittles is equal to the probability of male, then we would say male and Skittles would be independent, right? Or candy preference and gender really would be independent. So we're going to try it. What's the probability of male given Skittles? Well, male given Skittles, I'm going to just here Skittles. It's going to be 80 out of 140. What's the probability of male? Male is right here, which is 120 out of 200. So if you divide those and find what the percentages are, is the main thing you do. So 80 divided by 140. You get 57%. And 120 divided by 200, you get 60%. So it's pretty close. They're pretty close to as far as like if they're independent, and because they're less than 5%, you could honestly take either one. If this was an FRQ, you could say, okay, they're not exactly the same, so therefore they're not independent. Or you could take, you could actually take the route that because it's a less than a 5% difference that they would be independent. You might want to check another one to make sure that that's how they're going to be end up. But that's the way you could definitely go either way on this because of the difference is so close. But that's how you would show it. Another way, of course, you could show it is probability of male and Skittles is equal to the probability of male times the probability of Skittles. Again, if this is true, then they're independent. Well, male and Skittles is this one. So 80 out of 200, which we did, is 0.57. Oh, no, I didn't. This is 40%. And the probability of male is, we did that one already, is 60%, 120 over 200. Probability of Skittles is 140 out of 200. So if we did this and we said 120 divided by 200 times 140 divided by 200, we would get 42%. So again, they're super, super close. So I would definitely want to argue that these are independent, that there is a relationship between gender and candy preference, because these are super close. They're definitely less than 5%. These are really, really close. Close enough to be able to justify that they're independent. Next one, let's go to another problem here. Let's go to some multiple choice ones. Here we go. Okay, the probability that you win a prize in a carnival game is 1/7. During the last 9 attempts, you have failed to win. So I have done 1 minus 1/7, and I've done that in the last 9 attempts, 9. You decide to give it one last shot, assuming the outcomes are independent. What's the probability that you win? If they're independent, then the next probability is just going to be 1/7, because if I won, that would be 1/7. Right? This would be, what would be the probability of this happening these 10 times? But that's not what the question asks. The question says, what's the probability at that spot it happens? And that's the answer, is 1/7. A friend has placed a large number of plastic discs in a hat and invited you to select one at random. He informs you that you have half red and half blue. Probability is red, 50%. Probability of blue is 50%. If you draw a disc, record the color, replace it, and repeat 100 times. What's the following is true? It is unlikely you will choose red more than 50 times. That's not true, because I know it's going to be really close to 50, but it could be 51 or 52. So I would say that's no. If you draw 10 blue discs in a row, it is more likely you will draw red on the next try. That's not true, because each one's independent from the next, and so every single time you draw one, it's going to be a 50% probability, because you are replacing them. You're putting them back, so it's always an equal probability. The overall proportion of red discs drawn should be close to 50%. I agree with that, because it's large enough number that we're going to get a pretty close probability to the true probability, because obviously you do your NP, and that's equal to 100 times 0.5, which is 50. And since, remember, that's NP and NQ are both greater than 10, remember that my distribution is going to be pretty close to normal, and I'm going to get something that's really close to my actual probability. The chance that the 100th draw will be red depends. We know that's not true, because they're independent on the first 99 draws. That's not true. It says they're independent. It doesn't say they're independent, but we know they're independent because we're selecting them at random, and we're putting them back, we're replacing them. All the above are true. Okay, so that's not true. The two-way table given below gives information on males and females at high school performed on their music format. You select one student from this group. Which of the following statement is true about prefers vinyl and male? Okay, so it says the events are mutually exclusive and independent. Well, we know this is not true. Never can you have it mutually exclusive and independent. Let's just look at one thing. Mutually exclusive, for instance, they never overlap. Independent, they always overlap, and the overlap is equal to the product. So we know mutually exclusive events are never independent. The events are not mutually exclusive, but they are independent. Well, we can check and we can see. So it says we're looking for first vinyl, and we're looking for male. All right, so mutually exclusive would mean that they have no overlap. No overlap would mean that's a 0, so those are not 0. So that means they are not mutually exclusive. So I would agree with this part. Let's check if it says they are independent. Okay, in order to test for independence, we know that the probability of vinyl given male, I could have done male given vinyl either way, or vinyl given male, is going to be the probability of vinyl. So the probability of vinyl given male, so that means I'm going to be, I know it's male, so it has to be in this blue area. It's going to be the vinyl given male, that every single person in the survey is male. So it's basically saying of the males, how many like vinyl, which would be 48 out of 300. And this is going to be, is this equal, question mark, if this is equal to probability of vinyl, and vinyl is going to be 88 out of 550. If those are true, then they are independent, and B is a good answer. So we're gonna say 48 divided by 300 is equal to 16%, and 88 divided by 550 is equal to also 16%. So yes, indeed, they are independent. So B is true. And the other ones, I just like to read through them just to make sure I didn't make a mistake. Are mutually exclusive? We know that's not true, so we know that one's not true. Not mutually exclusive, we know that's true. And it says nor are they independent. No, we just showed that they're independent, so that's not true. The events are independent, yes, we agree with that, but we do not have enough information to determine if they're mutually exclusive. That's not true. So yes, I do agree that B is a good answer. Always make sure you go through all the answers just in case there's some sort of thing that you misread in your answer. And then when you read the other one, you say, oh, wait a minute, this is a better answer. And you read back at the other question and you see where you made the mistake. Okay, people with O negative blood are universal donors. That is, any patient that can receive a transfusion of O negative blood is 7.2% of the American population has O negative blood. If 10 people appear at random to give blood, what's the probability that at least one of them, is a universal donor? So we have the probability that you have O negative blood is 0.072. If 10 people appear at random to give blood, what's the probability at least one? So that means one person could be a donor, 2 people, 3 people. So we're going to do 1 minus the probability that we have no donor for 10 people. So the way that we're going to do this is 1 minus, remember, there's literally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all the probabilities obviously are the probability for no donor. And that's going to be, each one is going to be 1 minus 0.072. And okay, so because the probability of the opposite of that, right, is going to be 0.928. So this is just going to be 0.928 to the 10th power. So we have 1 minus 0.928 to the 10th power. So let's go ahead and do that. I'm just doing it on my calculator. 0.928 to the 10th power is, so it's 1 minus 0.4737 to get me about 52.6%. So it's C. A die loaded so that the number 6 comes up 3 times as often as any number. What is the probability of rolling a 4, 5, or 6? All right, so I basically have, this is my die basically, 1, 2, 3, 4, 5, 6, 6, 6. So this here is 3, or excuse me, I have 1, 2, 3, 4, 5, 6, 7, 8. Really what it's describing is an 8-sided dice because this has a 1/8 probability. All of these have each a 1/8 probability, but 6 has a 3/8 probability. So that's showing a situation where it's 3 times as much. So it says, what is the probability of rolling a 4, 5, or 6? So 4, 5, or 6 is just this here, 4, 5, or 6. So this is going to be 1/8. This is 1/8, and this is 3/8. So we're just going to add them together. And that's going to be 1/8 plus 1/8 plus 3/8 is going to be 5/8. You draw 2 candies at random from a bag that has 20 red, 10 green, and 15 orange, and 5 blue without replacement. So you're taking them and not putting them back. What's the probability that both are red? So I want red, red. So the first thing I have to see, I have 20 plus 10 is 30, plus another 20 is 50. So I have 50 total candies. So drawing the first one out of the bag is going to get me 20 out of 50. But then I draw it out, I don't put it back, and so now I only have 19 red left, but I only have 49 candies left. So that's how we would solve it. 20 out of 50 times 19 out of 49. So So I'm just going to do 20 divided by 50 times 19 divided by 49, and that's going to get me about 15.6%, which is this one here. And event A will occur with a probability of 0.5. So I'm putting it down. B will occur at 0.6. The probability that A and B occur will be 0.1. Okay, so it says A, the events are independent. So if they're independent, if independent, then probability of A and B, which equals to 0.1, will equal to the product A times B, which is equal to 0.5 times 0.6. But 0.5 times 0.6, of course, equals 0.03. Oh, sorry, it's 0.3, not 0.03. 0.3, so this is not equal to this, so they are not independent. Mutually exclusive. Mutually exclusive would mean that there's no overlap, and that would be that, so this is not mutually exclusive. Either A or B always occurs. So we know, well, we'll see the probability of A or B. So let's try that. Let's see what the probability of A or B is. If it always occurs and it would be equal to 1, probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. So A is 0.5, B is 0.6, but there's an overlap of 0.1 because 0.1, they both happen at the same time. So 0.5 plus 0.6 is going to be 0.11 minus 0.1, and that's equal to 1. So yes, that's 100% of the time. So yes, one of them will always occur. That's what that's saying. They're complementary. No, if they're complementary, then that means if A is occurring, B cannot occur, and vice versa. And that does not have that indication, because if one had the probability of 0.6, which B does, then A would have to be the probability of 0.4. And then none of the above is correct. We found one that was correct, so that's it. Event A occurs with the probability. By the way, guys, these two formulas, the probability of A or B is equal to the probability of A plus probability of B minus the probability of A and B, is on your formula chart, and then this is on your formula chart. A and B over B. That is also on your formula chart, so those you do not have to remember. Event A occurs with probability of 0.8. The conditional probability that B occurs given that A occurs, so the probability that A occurs is 0.8. The conditional probability that event B occurs given, so given A occurs, is 0.5. The probability that both occurs, so I want the probability that they both occur, which is A and B. So it wants me to just put my formula. So here's my formula. The probability of B given A is the probability of B and A over the probability of B, or A, sorry. And what I'm looking for is both occur, so B and A. And I know this here, probability of A is this, and I know the probability of B and A is this. So I'm just gonna put in 0.5 equals, I'll just put X over 0.8, and then I multiply them and I get X equals 0.4, so 40%. This, of course, is on your formula chart. This formula is on your formula chart. At Lakeville South High School, 60% of the students have high-speed internet access, so probability of high speed I'll just put is 0.6. Probability that they have mobile computing devices, M, is 0.3. And probability of H and M is 0.2. The proportion of students that have neither high speed nor is, so wants to know, basically it's doing this. We can throw this into let's throw this into a Venn diagram, just because it seems to fit for this question. So we know this is 0.2. This is my H and this is my M. So this is going to be 0.4 because 0.4 plus 0.2 is equal to 0.6. And then this one is going to be 0.2 plus 0.1 is equal to 0.3. Then if I add 0.4 plus 0.2 plus 0.1, I see that's going to be 0.7, so that means 30% are none. So that's going to be 30%. Another way, of course, you could have done this is the probability of H. You could have just used the formula that is on the formula chart. Probability of H or M is going to be probability of H plus probability of M minus the probability of H and M. That's just on your formula chart, and you would have said, okay, this is equal to 0.6 plus 0.3 minus 0.2, and that's going to get you to 0.7, and that's occurring one time or another time, and then so 1 minus that is obviously going to get my none. Experience has shown that a certain lie detector test will show a positive reading 10% of the time. So positive reading, 0.1. When a person, that's not finished, I guess. When a person is telling the truth. So positive given truth. So it's basically, it's wrong because it's saying it's a lie. So it's saying, hey, positive reading, and this means they told a lie. So basically is, that's not, you're telling the truth. You're saying, they say, are you Miss Brown? I say yes, and it goes beep, 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 and it says 10% of the time it says I'm lying. Okay? So then the next part says 95% of the time when a person is lying. So the probability of positive reading given lie is going to be 0.95. Suppose that a random sample of 5 suspects are subjected to a lie detector test regarding a recent one-person crime. The probability of observing no positive readings if all suspects plead innocent are telling the truth is, all right, so, okay, I am looking for 5 readings, as we said, and we're looking for the probability that none of them are positive given that's telling the truth. So essentially, it's opposite from this 0.1. So this is not positive. So negative, 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 negative. And so that's 0.9 times 0.9 times 0.9. The reason being is because it's the opposite of this, and they're independent, so we multiply them. So they're 0.9 to the 5th, which is about 0.591, and D here is our answer. Those are the answers. Hopefully we got it all right. So concepts, you can give your concepts your strengths and weaknesses. We can go ahead and look at this one here. So it says we have a following problems. Okay, so a simple random sample of adults in a metropolitan area select a survey and was administered a political reviews. The results are below. Okay, what's the probability a person chosen at random from the sample will have a moderate political view? Just moderate political views right here. That's it. So this would just probability of moderate is going to be 75 out of 255, and that's your answer. You can leave it like that. You don't have to change it to a decimal. You can leave it just like that. If you want to change it to a decimal, you're welcome to. What is the probability that a person chosen at random from those samples who are between the ages of 30 and 44 will have a moderate political view? So this time now I'm asking those who are between 30 and 44. So I'm asking the total for this time to be 85. So it's going to be the probability that I have a moderate political view given I'm between 30 and 45, because it said that is what I know, that they are absolutely those in the sample are going to be between 30 and 45. So all I have to do is put 30 over 85, and that's the work, and that's it. Based on your answers to A and B, are the political views and age independent? Why or why not? Well, I'm going to go ahead and divide them out now, because that's going to be helpful for me, because I'll show you why. Because if probability of moderate given 30 to 45 is equal to probability of moderate, then I can say that political views and age are independent. Now, my answers before staying in fractions were, that's fine, I was content with that. But now I need to go ahead and divide them because it's hard for me to tell if these fractions are equivalent by just looking at them. So I'm gonna divide this, and this one I get 29%, and this one I get 35%. So no, those are too far apart. So I'm gonna say no, because probability of this is equal to 0.35, and that's not equal to the probability of this, which is equal to 0.29. They're not independent.